So that's one example. Let's do another example. Let's see if we can use that same idea again. So here's a second example. What we're going to do is we're going to prove that n squared plus 12n is in, or is, big O of n squared. Now you might ask, Dan, why are you picking n squared, not n? Well, remember, I'm pretty sure that it won't work if this is n here. I'm not in this stream going to show you how you prove that it doesn't work. That'll be something I'll do in the future. But I want to just show you here that we're going to try using the same idea again. But we're going to extend this a little further. And by doing this, I'm going to show you actually a more general strategy that actually comes out of the idea that I showed you in our previous example. So I want to make whatever's here look kind of like that. So I have something that's n squared plus 12 times n. I want to do something with c to make it so that this thing looks a lot like that. And if I am able to bound the inequality correctly, we're done. So let's write out a proof. So remember the game plan. Remember the game plan. We want to find c and n0. Our job is the inequality comes from the selections of c and n0. That's the part where we actually have to justify our constants that we select. So here's our proof. We need to find constants c, which is a positive real constant, right? And n0, which is a positive integer, such that, gotta make sure I put my comma in, need a comma, such that for all n greater or equal to n0, what do we want to do? We want to say that n squared plus 12n is less than or equal to c times n squared. Now this looks a little different than our previous example. Why? Because there's two terms here. What I would like to do is I would like to take this n squared and try to make it look kind of like this, but make it so it's bigger than what's on the left-hand side of the inequality for an appropriate value for n or greater. Does anybody see any idea like the one I used last time? Well, I have n squared, and I have 12 n's here. Maybe if I make 12n squared terms here, maybe I can create something that looks like that. So I'm going to pick, you're going to see why 13 works really nicely here. Pick c is equal to 13. Now this is the major observation I'm going to have in my proof. Notice that for all n greater or equal to 1, we have the following chain of inequalities. Now, chaining of inequalities looks a little daunting at first, but don't worry, it's not actually that complicated. I'm going to show you what kind of reasoning I'm using with a demonstration shortly. So I'm giving you my backup here. So this is an observation I'm making in my proof. This observation is what gets us to the conclusion. Notice that for all n greater or equal to 1, n squared plus 12n is going to be less than or equal to n squared plus 12n squared, which is of course equal to 13n squared. Now, I haven't yet justified why this is true, right? You have to make sure when you write something down like this, you need to justify it at some point. Now, this part is obvious. I say the domain, I'm saying that this statement is true, and I'm going to give you my reason why now. As n squared is less than or equal to n squared for all n greater or equal to 1, and 12n is less than or equal to 12n squared for all n greater or equal to 1. Now, if you take a look at these two simpler expressions, what I do is I'm going to add them together. I'm going to add these two inequalities, the terms on both of the sides, to each contributed side, and that's actually how I get this statement, this chain of inequalities here. How do I know that this statement is true? Well, if you divide both sides, because remember, I'm assuming that n is positive, right? So if I divide both sides of this by n squared, I end up with 1 is less or equal to 1, which has to be true for all n that are greater or equal to 1. Then, notice that I have 12n is less or equal to 12n squared. Notice that if I divide both sides by 12n, I end up with n is greater or equal to 1, right? So that's how you could justify these if you want to break it down into further steps. Now, I want to show you exactly why this all works the way it does. So I want to show you where this comes from. So I find this is easier to explain using actual things. Okay, now imagine I was trying to show you that two statements of quantities were equal to one another. Now I have two buckets here, and I have some objects. They're all the same size, they're the same objects. So just imagine these as quantities. You'd agree with me that if I put one of these bottles into one of the bins, and I put one of these into the other bins, you'd agree with me that they have equal quantities, right? They have equal quantities. You'd also agree with me that if I added in another pill bottle, whatever this is, into another one in each one, you'd agree with that the quantities are still equal, right? If I took and totaled these up, right? So each one has 2 in it. Just like if I had added another one into each one of these again. Okay, you'd agree with me that that makes sense, right? It's coherent. It's sound. I'm going to use the exact same type of reasoning. So it's a similar setup to what I'm doing here. So I have, these are my two buckets. This is my left, this is this bucket, this is that bucket. Now, if I know that they're equal terms, it's no different than like if I stick one of these each in each bucket. But if I know that one other bucket, say if one side of this inequality actually contributes more, then we know that that side is at least the amount on the left-hand side of the inequality. So for example, if I have 1 here and 2 here, you'd agree with me that the ones in this bucket are at least, is going to be no more than what's in here, right? So in fact, if I switch these two around, it's kind of like if I had these two inequalities here. So all I'm doing is I'm adding up the two sides of the inequalities together to get two kind of super inequalities. So I'm just summing over two inequalities, this one and that one. So I'm just taking n squared, and then I'm adding 12n and 12n squared. 12n on this side, 12n squared. So I'm just summing over the inequalities, because I know that this is less than or equal to that. In fact, they're equal, so different than me putting these in here. However, the second one over here, it's very possible that the right-hand side of that inequality is going to be larger. It's no different than if I took 2 of these pill bottles and I put in one in here. So it's really just the same idea being applied. Does everybody see that? So it's actually not that complicated. So just remember, the reason why this works is I'm summing over inequalities. So I've taken each bit in piece comparatively. So I have the n squareds, and I have the 12n and 12n squared. I sum each one of these inequalities together. I sum over these two, and that's how I conclude and get this statement. So all I'm doing is I'm just taking quantities of equal or greater amounts, and I'm dumping the one into the larger bin than the other one. It's really just that simple. So if you understand this reasoning here, we can generalize this further, right? I'm going to show you how you can generalize this even further with a more complicated example. But I just want you to observe that I'm using this kind of bucketed inequality approach. It's not the technical name for it, but I like to think of it like I have this term and I compare it against that term. And I have this term and I compare it against that term. If I add this to that, I add both inequalities together, their respective left and the right sides, I end up with this chain of reasoning. The 13n squared, this is c right here, right? What's n0 then? What's n0? n0 is 1, right? I just told you it. It's right here. Notice that for n greater or equal to 1. Choose n0 is equal to 1. I'm just going to switch markers here. Therefore, by the definition of big O, n squared plus 12n is big O of n squared. And we're done. So the core of this argument, notice I didn't do any crazy analytics with you or anything like that. All I did was I compared terms, and then I added up the terms. Because you'll notice that I have this. I know this is going to be less or equal to that. And I have this. I know I demonstrated that's less or equal to this. I broke it down into simpler pieces, then I just added them all together. Easy peasy stuff, right? Notice that I didn't need to do any root solving or anything like that. I didn't make any assumptions about the functions increasing or anything like that. Those are some assumptions you can make to do some other techniques like root solving, which is another technique that some people like to use when they're proving claims like this. Okay. So let's do another example. I'm hoping that you're starting to see a pattern.